All right, welcome to Introduction to Machine Learning. I'm Sundeep Rangan at New York University. So this is the 5th unit on LASSO regularization and feature selection. Feature selection is really one of the most basic tools in machine learning, which tells you about roughly what features or what variables you should use in your problems. So in today's unit, I'm going to try to define that feature or model selection a little more carefully. I'm going to show you how to mathematically formalize that with a technique called regularization. We're going to show you how to pick regularizers, do some of the basic mathematics or operations for fitting with regularization using some Python tools, and then I'll do a little bit of a probabilistic interpretation and show you some other feature selection methods as well. So let's dive into it with a quick example or motivating example. So you'll see that now there are many services that try to predict house prices. You might be familiar with Zillow, or if you're in New York City, you might see Street Easy. And if you go to Zillow, for example, and you look up a house, you get something like this. So this is a beautiful house in Portland, Oregon, and the seller is selling it for $458,000. But if you zoom down, there's also a number this website gives you called a Z estimate, and it says that the actual market value for this house is $461,000. So Zillow thinks that this is a pretty fair price for this, and it actually tracks the value or an estimated value over time. And so this means these kind of estimates that data science is very much entering real estate like it's entering all fields now. And in fact, this picture that I took is from this great article on the new algorithm that Zillow is using to compute this estimate. Now, if you think about this problem from a data science perspective, one thing that is overwhelming is that there are a lot of variables, obviously, that go into determining the house price. The size of the house, the condition that it's in, maybe some neighborhoods are more desirable than others, or the school district, or maybe even other impersonal things about quality or some aspects of the house. And then the question is, how can you determine this? Or today's lecture, or this unit's lecture, is about what variables I should try to use to make a good judgment, and what variables should I not try to use. So to do this, we don't have access to Zillow's entire database. So we're going to use a much simpler database that comes from this great paper by Dean DeCock, which looked at sales in Ames, Iowa for about a 4-year period. So if you did Unit 2, I think it is, you might have seen the very, very simple classic Boston housing data set. That's actually a very simple data set for predicting house prices. This one's a lot more interesting from our perspective, because for each home sale, there's about 81 variables. And we're going to see from this really large set which ones we can pick and which ones we can try to discard. With that, let's dive into a demo on the GitHub website to continue. Okay, as before, I've placed a very simple demo to illustrate these concepts on the GitHub site. So you can, again, download the entire GitHub repository. Remember, if you're watching this on YouTube, all the information for this class and this unit in particular is below. But if you don't want to download that repository and run it on your local machine, just go over to colab.research.google.com and click GitHub. Select my GitHub page as we did before, which is github.com/sdrangan. Go to the repository, intro ML, and go to the 5th unit And here it is the second demo. There was an earlier demo which I used the prostate cancer dataset from the class, but I think this one is a little more illustrative. So click on that, demo to housing, and then the demo should load. Okay, so let's just start off right away here with loading the basic packages as usual. It might ask you for the first time whether you want to run the commands. All right, now let's download the data. This command here will download the data from the GitHub site onto this virtual machine. You actually don't need to run this command if you were running this on your local machine, but if we're going to run it virtually, we have to run this. So now it is in the virtual machine, and then given that it's a CSV file, we just load it with pandas. So here we can take a look at a little bit of this data. I've just printed the first 5 columns. And one thing that becomes really obvious is that there's a large number of features. The zoning type, the lot area, some utilities information, the slope of the land, the neighborhood, and so on. There's about 81 of these, in fact. All right, if you look at the total size of this data set, we have about 1460 samples and 81 features. Now, the first thing we want to do is that you'll see that some of these features have missing values. So they show up as NaN. Now, there is a lot of ways to deal with missing values, but just to make this simple, I'm just going to use this drop NA command to just remove any feature where there's at least a single missing value. That's not the best thing to do because we're kind of throwing away a lot of data, but let's just do that to make it easy. And when you do that, you're down to about 62 attributes per sample, but still plenty enough to have an interesting model. Now, the other aspect that's suggested in that de Kock paper was that we should try to look at only the houses where the sales condition was normal, as opposed to being on foreclosure or something like that. So I'm just going to do this little bit of pandas syntax to do that. And after that, we're down to little under 1,200 samples. So we still have a lot of data and a lot of attributes. Okay, let's start looking into these variables a little more. Before we do the fitting, we need to do a little bit of, let's call it data cleaning. So first thing to notice is that if you look at these variables, they're different types. And some of them are real values or integers, but some of them are this object type. And object here are the categorical variables. So for example, if you look at zoning and you go back here, you'll see that it's given a type, like the first 5 types here are RL. Or lot shape, it's regular or IR1. I'm not actually sure what that stands for. Or neighborhood, it's one of these neighborhoods. As opposed to real values like the lot frontage area or lot area. So what we need to do is try to encode all these categorical variables as numerical values. And if you recall back from, I think it's unit 3, when we talked about multiple linear regression, the most simple technique is to use one-hot coding. That's done so commonly, Pandas actually has some very good tools to do this, mostly for us. The first thing we need to do is identify all the columns that are categorical versus, let's call them real valued variables. And that's what this little bit of code does here. I create 2 lists and I go through all the columns, and if its type is object, I add it to the categorical variables column. If it's otherwise, I add it into the real variables column. And then you can see all the categorical variables here and all the real variables here. Then we use this great little pandas routine called get dummies. And we take, well, first of all, we get the columns of the data frames corresponding to the real variables, and those to the categorical variables. And then we use this get dummies routine here, which one-hot codes all the categorical variables. So just to give you a picture of what that looks like, if you look at, for example, let's take a look here at the original categorical data frame. So it had like zoning, which was RL. But when you look at it in the encoded version, you see that that MS zoning is replaced by 1, 2, 3, 4 columns. So if the value is RL, it gets a 1. Otherwise, it gets a 0. So on any entry where it was FV, it would get a 1, and so on. And you do this to all these categorical variables, and it's replaced by a giant 0, 1 matrix. This time having here 142 columns. Then I join the real variables with the one-hot encoded categorical variables, and that gives me my final data frame. And in this case, you see that it still has 1198 samples, but now there are 174 variables of interest after all this one-hot coding. So we have a lot of possible variables to choose from. And that's the key thing. We'll also get the targets. Now we need one little bit more of cleanup, one more step before we can perform our regression. First thing is, like always, we do a train test split. I'm just going to use about 30% for testing. Here we're using our train test split function from before. Now the next thing you need to do is you need to scale the variables. Now why do you need to scale the variables? Some of these variables represent very different units. So you could imagine, for example, house price being in the hundreds of thousands, or the area being in the hundreds or thousands of square feet, whereas some other variables might be just 0 or 1. And if you want to make any sensible prediction, you have to put them all into the same scale. So what we're going to do is we're going to create two scalar objects in Python. Like I think we did this before in Unit 3. And we'll fit the scaling on the training data and then apply or transform or rescale both the training and the test data. This particular scalar, the standard scalar, just subtracts the mean and divides by the standard deviation. So they're all kind of in the same range. And it finds that mean or the standard deviation, and the standard deviation on the training data. So let's just run that. That's very fast. Now we have everything clean. We've got the data, all the missing values are removed, all the categorical variables are encoded, and everything is nicely scaled. Let's go ahead and try to see if our just simple linear regression works. All right, that is very easy. It's just in Python, they make it super simple for you. All I'm going to do is I'm going to call a linear regression object, or create it, fit it on the training data. I'm just going to measure the R-squared value on the training data and the R-squared value on the test data. And let's see what happens. Okay, remember R-squared is a number between 0 and 1. If you get close to 1, it's very good. And on the training data, we get an R-squared value of about 0.93, very close to 1, actually 0.94. So all but about 6% of the variance in the training data looks to be explained by these 174 variables. But when I go to new samples on the test data, it's just completely crazy. It's close to infinity. Basically, it completely blew up the calculation. Now, you might wonder what happened. Why did it fail so spectacularly? Well, there's one more thing we need to correct. So if you remember back from Unit 3, the way that you compute the least squared solution is you construct this matrix A, which has the transformed features in it, and you have to compute this matrix inverse of A transpose A. Now the problem is A transpose A may have some eigenvalues mathematically that are close to 0. So when you try to invert that, it blows up, and that's exactly what happens here. Now, in the case when you're looking at the training data, it doesn't matter because the directions in which it blows up are not present in the training data. But whenever you give it a new sample, it could easily excite one of those directions and give crazy predictions. So basically, in some ways, it's kind of overfitting the data. It's finding directions which were just not valid in the general data set. So let's do one simple thing, and that is to do a little bit better conditioning of the data. And what you do is that instead of doing this inverse, we add this small term here. And that just ensures that all the eigenvalues are a little bit greater than 0 with a small value of alpha. Turns out that this technique is also called ridge regression, which I will return to later, but now just think about it as a conditioning technique. And so to do this, Python also has a tool for this, and I just tell it the value of this little small value I should add to make it better conditioned. All right, so I give it ridge, I fit it, just same syntax as before, and then I predict on the new data set and measure the test. And it's about, this case, about 90% or 0.90. So it looks pretty good. We're getting about 90% of the variance. We can look at the predictions. The way to do that, remember that we scaled the output. So if we want to look at it back in the original units, we have to perform an inverse transform. So we're going to take those predictions and look at the inverse of that, and then plot the predicted versus actual. So if the predicted was perfect, it would sit on the orange line. But we see here that it's pretty close to that for most of the points. Doesn't seem to predict kind of as a limit. Some very high values get mispredicted. And it gives, a couple of outliers. Like it gives a negative prediction. But for the overwhelming majority, it does a pretty good job. But if I come back to my original question, which is what features mattered and what features didn't matter, it's not so clear. So to see that, let's take a look at what the model thinks are the 10 most important features. But what do we mean by most important? Well, one idea is to look at the coefficients, which are just the 10 largest ones, because remember all the variables are correctly scaled. So we can do that here. If you go back to our regularizer object, you can get the coefficients and convert it to a vector. And I'm just going to sort them along their absolute value and just literally print the names of those variables. So kind of reasonably, it tells you like the overall living area is very important, but there's some slightly odd things. It tells you the overall living area is important, but so is the second floor area. And these two are highly correlated. So it's not obvious that if you removed one, whether you would still get a good prediction. You'll also see a lot of variables that are also slightly correlated, like kitchen quality and the external quality. Now, there's also a lot of problem if we say the opposite question, like which variables don't matter. So to do that, I could say I'm going to look at the smallest coefficients. And this figure, though, shows the following. On the left, I have plotted all the coefficients in the order of the variables. So there they are. I think there was about 70 or so of these variables. And I've also here plotted them in a sorted index. So you see a few are large, but you don't see that any are really small. I mean, they get lower, but they're not, they're only about 5-6 times smaller than that maximum one. So you'd be a little hard pressed to start discarding these variables, given that they are still having an effect in the model. So what the conclusion is that if we don't do conditioning, we get overfitting. So we need to do some conditioning. But even after we do a little bit of conditioning, it's not obvious that which are the variables that are important or the variables that can be discarded. What I'm going to show you in the rest of this unit is a technique to really better identify those features that matter. But before you do that, just so that you're familiar with this data set, I want you to do a little quick in-class exercise, which should be pretty easy.